This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Okay. Today, we're going to be looking at, it's a bit of a mouthful, but we're going to look at hierarchical state machines. In particular, chapter 5.2 in the text. What I want to do is I want to give you a big picture reminder of where we're at in terms of describing discrete systems, okay? We use state machines to model complex behaviour in a fairly simple way, right? Just some bubbles and some arrows. And when we start adding some complexity to them, they can describe more things. For instance, we can add variables to our state machines and they become extended state machines. And then we can use concurrent composition to bolt together, side by side, cascade connection, however you like, multiple state machines to make even more complex models. And we can also go the other way and break down a complicated machine into several sub-blocks, as we'll see when we look at hierarchies. But the idea behind making more and more complex state machines is that we have to be unambiguous about how it works, right? We have to be able to specify a state machine so precisely that a machine that is much smarter than us in terms of computational power can take that machine and perform an analysis on it. There's no ambiguity. The machine can't come back to you and say, I'm not sure what you mean by transitioning between these two states, or under what conditions could this happen. So we're going to be even take this a step further when we look at hierarchical state machines today, okay? All right. What I'll do is we'll just recap some of the composition methods we've seen so far, and then I'll motivate hierarchical composition by an example that we've seen before when we looked at interrupts. Okay, so what does synchronous composition look like? So here are two state machines. They're independent, but if I want to compose them together into a synchronous model side by side, then I can lump them together into this overall state machine C. Now, if I go back a step, remember that, and I've had a few people ask this to me, remember that a FSM diagram describes what happens, what the machine does, right? It doesn't say anything about when that happens, okay? So a state machine diagram tells you what the state machine does, but it doesn't tell you when. When does it happen? The environment decides, okay? What's the environment? Well, the environment might be a tick of a clock. It could be someone coming and pushing a button. It could be a pedestrian pushing a button on a crossing. It's the environment that decides when the particular transitions are taken. This just tells you that the conditions under which they're taken, but not when. Okay, I've got to keep stressing that to you. So when you have a composition, so here's two independent state machines, and you compose them together, the environment still determines when they react. Yeah? Right? There's nothing in here saying about when these things react. It just tells you the conditions under which they will react, not when. So the environment still decides when these things are going to transition. Okay? But we have a little bit of flexibility in how we compose these in order to sequence how they respond. Okay? The environment's still making the system react externally to us, externally to the modelling here, but we have a bit of a choice. Okay, and one of the choices is synchronous composition. Okay, and I'm going over this because I have to point out why we can't use it for an example that's coming up. So remember, synchronous composition is that in side-by-side model like this, both state machines react simultaneously in lockstep to reactions. So if we have default states S1 and S3, in this case we have guards all being true here, right? So those transitions are always going to be taken. When? Who cares? But they're just going to be taken at the same time, okay? Because they'll both evaluate to true when there's a reaction. So we know that we compose this sort of, conglomerate state, S1, S3, and when we get a reaction, we then, both machines transition in lockstep, okay? So our synchronous composition looks fairly simple, right? It's just this S1, S3 to S2, S4 combo and back and forth. Note that the other possibility of having S1, S4, S2 to S3, that is still a possibility of transitions occurring between those two states. They're in lockstep still, but there's no way of actually entering those states, assuming that we have default states of S1, S3, or initialized states of S1, S3. Okay, so the composition of the set of states, if you want to think of this as the set of states of this new composition C, is equal to the cross of the set of states of A and B. In this case, it's fairly straightforward. We've got two states in A, two states in B, so the set of states of C is 4. But you can be a little bit more pedantic about this if you like, and say that so if I cross out that equal sign, it's probably bad drawing over the top, but I can say that it's actually could be equal to the space, or it could be a subspace of that, okay? In that, if these two states are unreachable, we can essentially remove them from the diagram, okay? And we are left with a composition that's only two states. So 2 cross 2, well, 2 is a sub amount of states of 2 cross 2, okay? So we can formally show that side-by-side composition in synchronous composition is actually equal to just that. That's a formal way of showing it. Okay, that's a fairly easy one, right, when things are in lockstep. But when we deal with asynchronous composition, we've got some decisions to make about how we represent what happens. And this, as I said before, kind of gets people a bit messed up thinking about it. So immediately, that if I want to compose these into a new state machine, D, well, call that D, that I need some sort of semantics about which machine reacts. Because they're not going to react in lockstep, then is there some sort of system where A reacts before B, B reacts before A? Are they allowed to react at the same time? Even asynchronously, right? They could still, it could be A before B, and then the next time it could be A and B at the same time. There could be some mechanism that they are reacting like that. And typically what we do is when we have asynchronous composition, we use what's called interleaving semantics. And so essentially we are choosing one of the machines to react non-deterministically, then choosing another, then choosing one of the machines, then choosing one of the machines, then choosing one of the machines. And so what that does is you can see it just blows out the potential space of states here. So we've got the full complement here, 2 cross 2. We've got 4 possible states, and we've got transitions that are going between these dependent on which one you chose to react, okay, first, basically, right? So clearly here, B is the one that's responding to a reaction, and then maybe A might that time, and then maybe A again, okay? And we draw these arrows with red arrows to show it's non-deterministic, right? We know that these are possibilities. Which one it takes, it's beyond our control in here. There's no probabilities associated with any of this. Okay? We just say it's the environment will decide which one is actually taken. Okay, all states are reachable in this particular setup here. So we have a bit of choice about how they react by picking interleaving semantics. It gets really complicated if we actually have asynchronous composition where we can allow A, B to occur at different times and also at the same time. It gets complicated there, okay, because we could have outputs perhaps that are not compatible with each other and things like that. It starts getting a bit messy. So typically we choose these interleaving semantics. Okay, so let's motivate a new type of composition by showing that synchronous and asynchronous composition is bad for this, well, not the right way of modelling this example. Right, here's a familiar bit of code. When we were looking at interrupts previously, we kind of traced through this code before. It has two regions, if you like. Oops, I grabbed some global stuff here. You have one function here. I can't see where that curly brace is. Hang on. Oh, it's over there. And you've got one function here. So you've got... Sorry, my toolbar was covering some of the code. Right, so you've got an interrupt service routine. That's the top section, and you've got some main function. Now, this code is supposed to do something for 2 seconds, but there's a timer that's giving us the timing information, right? And what it's doing is it's basically ticking every 1 millisecond. So in our little main code here, we do some stuff. We set up, for a particular architecture, the location of the interrupt service routine, right? We tell the microprocessor, right, the interrupt service routine lives at some memory address, and every time you get a tick of the clock, which you may have initialized as some rate somewhere else, that you are going to branch to this piece of code here. Okay, that's how ISRs work. We're going to initialize a variable timer count to be 2000. Then, as long as it's above 0, well, it's not equal to 0 technically, we are just going to run some code in here. Now, what happens? Well, every 1 millisecond tick of that timer, we are executing the interrupt service routine. Right? So there will be a whole bunch of instructions in here. Every time an interrupt comes in, bang, we jump up to here, branch up to here. And it's very simple. We had a little condition here to make sure that the timer count's not equal to 0, so we don't decrement below it. Otherwise, just subtract 1 off there, because we've had an event. Okay, so bang, take 1 off the timer. So this code should obviously, you would think would run for 2 seconds, because as stuff is happening, right, the interrupts are coming in, it's externally, if you like, ticking down this timer count variable, which is up here, and eventually, when we get back to here and we check that condition, we will break this while loop and move on. Okay, so is this code correct? That's an interesting statement. Is it correct? What do I mean by correct? How do we measure correctness? Okay, so we could sit there with a stopwatch, right, somehow, and try and time this segment of code executing for 2 seconds, right? That's one way of doing it. Let's think even simpler than that. Let's say our measure of correctness is that loop just breaks at all, right? It gets out of that loop eventually. So we're not even worrying about 2 seconds. It's just going to get out of that at some stage. So we're going to measure correctness by the code getting to there. The processor executing instructions, getting to the blue arrow, right? let's not worry about the timing. Let's just say if it gets to there, we'll assume it's counted for 2 seconds. If it doesn't get to there, something's wrong. Okay, so that's what we're going to define as correctness of the code. So how do we do that? We could look at this code, and we will, as a state machine. Okay? Why? Well, any computer can be modelled as a state machine. Okay? Think about a typical, well, a von Neumann architecture computer. Its state is its memory. Okay? So the state of the computer is all those ones and zeros sitting in the entire memory space. If we think maybe keep it to an embedded processor because it's too much stuff going on a computer, it's all the ones and zeros in the flash memory on the microcontroller. Right? That's the state of the system. The update function, if we remember how state machines work, it updates the state, right, to the next state. It takes all those ones and zeros, takes the inputs, and maps that to a new set of ones and zeros, right, and new outputs. But we've got a bit of a problem. If you think of the memory space of a basic, even a little processor, maybe with a couple of gig memory, and that's gigabytes memory. So I've got to multiply that by 8 to get the amount of bits that are in there. And then we think of this as some crazy state machine where we have to think of all the mappings from all the bits to all the possible other bits that could change. It becomes completely intractable to even think about how you can map all combinations of ones and zeros in a massive memory space to all the other possible states that it could be in. There might be some unreachable ones, but it still just blows your mind. So we can't really kind of do that in a brute force way of thinking about this as ones and zeros and states like that. Instead, we're going to be a little clever. And we're going to choose state, not necessarily as in like the real state of ones and zeros in the memory, but we're going to choose state by where we are in the code. It's strange to think of it like that. But let's run through it and see how that plays out. So let's pick out important bits in the code where maybe we can think of as particular states of the execution of the code. So my damn toolbar is in the way. Right, so 5 points are chosen here. 3 in the main function and 2 in the interrupt service routine. So remember, now the question is still, will we get to C, right, after this little 2-second loop? Will that even work? Will that even execute? That's just our correctness measure. Okay, so how would you do this? Can you do it formally? Now, most of you would look through this code and say, okay, I'm going to go into the main function and I'm going to keep in my head a timer value. And then obviously it's not equal to 0, so I'll check the code in here. And then if an interrupt comes, well, it's a bit tricky because, well, interrupts are an external mechanism, but okay, I can reduce the timer, etc. So you would look at the code, you would think through the flow of it all, you would think through all the branches that are happening in your head. You'd hope you thought of everything that could happen, and you might get lucky. Maybe you can somehow prove that it'll get to C or not. But that'll only really work for trivial cases of code, right? And that's still not really a formal process. You've kind of sort of done it in your head and roughly written some stuff out. To formally go and show that to someone that you can get to C, that it doesn't exist. It's just your notes and drawing some stuff perhaps. So for a complicated system, this way of sort of analysing the code in your head and running through it, stepping through it's not going to work. Okay, so we're going to formally determine whether or not this code will work and under what conditions that can happen. Okay, so the first step to doing this is representing these two functions as state machines in themselves. All right, so let's stick with the main function first. And we're going to use 3 states to represent those particularly important areas in the code where we will be up to. Now, we're going to model this as an extended state machine. There's a variable. Obviously, there's a variable in the code floating around, so variable in the code. And it's important to note these arrows are properly aligned, okay? They're not supposed to point to instructions. They're at the point just before the while loop. Okay, think of it that way. So here, right, we can think of, okay, we've got an initialization. We're going to start off the whole process as A. A is the first important state. There might be some other rubbish going on up here, but A is the one that we're worried about because we're worried about the execution of this loop. All right, so what happens? So, well, we enter the while loop, and so while the timer is not equal to 0, so we make a transition to state B. Now, state B could be actually, you know, you could dive into that, multiple things happening in there, but it's just a state where the code is running in the loop. We've abstracted it to that level. There's stuff happening in the loop. At some point later in time, remember that if we have unguarded transitions, it essentially means that it's true, right? So at some later point in time, this machine will react and we'll get back to A. In other words, all of these instructions have run and we'll get back to A again. Because that's how while loops work in C, right? You get to the bottom of the code and you've got to go and check your condition again. So it jumps back to here and checks its condition. If it's not equal to 0, then right, it's going to be looping for as long as it wants. Does anyone have a problem with this true sitting here? There should be no problem. FSMs like this have no timing info in them, right? How long is it in state B for? Don't care, right? We just know that eventually it's going to cause a reaction to get out back to A. Okay, no timing info. And indeed, C doesn't have any timing info in here either, right? You've got a whole bunch of instructions. It doesn't tell you it takes 2 seconds or 1 second to do or half a second. It doesn't tell you that. Okay, finally, if we're at A and we compare timer count and it is 0, then we don't execute the while loop, clearly. And then, therefore, we end up in state C, which is where we want to check if we can get to. So I think the main part of the code is really fairly straightforward. But what about our little ISR up here? How are we going to represent that as a state machine? Now, we're going to start off with a default state of idle. Now, what does that mean? It just means that it's neither in D nor E, okay? So if you remember, think about the state being that the program counter of the computer or the processor is at this point here. We need some sort of indicator to indicate that the ISR is not even being run. All right, it's not in D or E, so we're going to call that idle, right? The ISR is not active. And that's the default state. Now, we're modelling this as a composition that's going to have some input called assert. So that's telling us that an interrupt has been asserted, right? Call it interrupt, call it assert, whatever you like. And if that happens, right, we branch to the ISR. That's great, we're in here. And therefore, we end up, after maybe disabling some other interrupts, end up at point D here. So at point D, if the timer count's not equal to 0, we take the conditional action here, which is to get to E, right? Which basically then subtracts 1 off the timer, which is a variable, and asserts return, right? In other words, and you obviously then escape the interrupt code and end up back in the main bit where you were. Now, so that was that transition there, right, when timer count's not equal to 0. Otherwise, there's a default transition because the guard is true here, So if this is not satisfied, then you just go back to idle. In other words, you don't subtract because you're less than 0, or well, you are 0 or less than 0. Okay, so that's how this little these two little state machines work independently. What we want to do is we want to compose them. Okay, let's compose these into a more complex state machine that represents the whole behaviour, because at the moment they're just sitting there by themselves. The question is, and I think it's up here, how to compose them. Are we going to compose them? So note also, I should say, that the only thing that's common between these is a variable. So there's a variable being shared, right? So we're going to do a side-by-side composition, I guess, of them, or yeah, because, well, there's no inputs going to outputs of the other one, right? So do we do it synchronously? So are these machines going to be going in lockstep with each other, transitioning states? Or are we going to do it asynchronously? And the answer is no to both. We're not going to do either. Why aren't we going to do either? Synchronous composition has a bit of a problem. So if we allow these two things to go in lockstep, you could imagine that if we're in, say, idle for the ISR, and we're at point A in the code, and we get a reaction, so this reaction is allowed, right? Timer count's not equal to 0, and at the same time an interrupt comes in. Okay, we could technically have our state machine going from a combined state of A, idle to B, D. Now we know that's not how computers work. You can't be executing some instruction down here while you are also executing something up here. Right? Computers can't process two things at once. So we can't allow synchronous composition. It's not going to work here. So what about asynchronous composition? Can we allow one to react at a different time to the other? The answer for that is, again, no, we can't do that. And we can't do that because this isn't how interrupts work, right? We can't, say, be inside the ISR here, and upon a reaction coming in, react in the main part of the code either. Right? That doesn't make sense, right? The way an interrupt service routine works is you service the interrupt, and when you are finished, you then go back to the main part. You can't kind of be in the middle of the ISR and some sort of reaction occurs, and then you skip states in the main program. That doesn't make sense either, to do it asynchronously like that. So we've got a problem. Synchronous composition won't work. Asynchronous composition, at least with interleaving, won't work either. So we need something else. If you're interested, that is the asynchronous composition of this machine. There's two machines. Right? It becomes messy. We've got to enumerate all the possibilities, allowing one or the other, machine A or B, to be able to react. And as I said before, we get transitions that shouldn't happen, right? So if we enumerate all these possibilities, right, of either machine reacting, let's look at one of them in particular. Let's say we're in state AD. So in other words, we're in the main loop, main function here, and we are in the ISR. Okay, so the state is here and the state is here. We can never have a transition going from AD to BD, right? Because we can't increment anything in main while we are servicing the interrupt, as I said before. It makes no sense, right? A computer can only issue instructions in a particular order. It can't be sort of doing stuff in weird orderings like that. Okay, so no, won't work. Can't allow this. So what do? We need another method for composing these two that will represent the behaviour of how this works, this machine works. But In order to do this, we need a better model of the hardware. And this is a better model of how an interrupt controller would work. So we're stepping back from the code for a second. We're thinking about how an interrupt controller works. There's a complicated interrupt controller. It has a whole bunch of, present or not present inputs here, right? Very simple binary inputs here, and an output. And it has 4 states. I'm not going to go on too much about this machine because it'll get way too complex for our needs. But you can think of how an interrupt controller works is that, well, there's a state where it's inactive. You might get an interrupt come in. You go to a pending state where you're ready to actually service it. If you are available to handle it, right, you've got the resources to be able to handle it, you go and actively handle the interrupt, right? You can also have additional ones coming in and you go to another state which might keep track of the fact that you're servicing one but you've got another one pending. And if you start servicing them, you can get rid of the pending part, or you could get out of the one you're currently servicing, go back to pending, etc. Right? There's a lot of transitions that could be possible here. You're active, you finish servicing, you go back to inactive. But it's all it models it nicely, but it's going to make our composition quite ugly. So we're going to keep it simple, and we're going to forget about pending interrupts. Like while we're servicing, one comes in pending, we have to remember it. And therefore what that means is we can just, I thought that was going to come. We can just essentially, if we don't worry about having multiple interrupts occurring at the same time and being able to handle them, we'll end up with just 2 states. It's either inactive or active. Okay? The interrupt handling mechanism is either inactive or it's active. If it's inactive, then some other main code is running. If it's active, the ISR is running. But first, we need to describe how this works in this a new framework called a hierarchical state machine. It's fairly simple, but we can start getting bogged down in detail again about which one is going to react in the composition. So this is a very simple 2-state state machine where state B is actually a refinement of 2 other states. We call that a refinement, right? It's like you're abstracting it. So you could just look at this from a top level and you zoom in, and inside B there's 2 states in here. Indeed, this is exactly how you can represent the state machine, the default state machine for the Kabuki in C works, right? You've got an idle and a running, and inside the running you've got some other actions that might happen inside here. Okay, so when do things react? So firstly, we're going to say that the refinement of the current state, so this is the refinement of state B, reacts. Then we'll say that the top level machine reacts. And if they both produce outputs, as we'll see very soon, we have to make sure that the outputs don't conflict. So for instance, we can't have this refinement here setting an output to say a binary 1, and upon a transition to here, it sets it to 0 or something like that. We've got to be really careful about outputs that way. But it's important to mention that these 2 steps, even though it looks like there's some sort of ordering here, they're considered to happen simultaneously and instantaneously. If that doesn't worry you, why do we do that? It's because when we look at feedback, we actually need to know the outputs, right, in order to know the inputs in order to be able to change the state. So we do have a little bit of ordering here, but it's considered to be the same reaction. It might look a little clearer when we look at a trace through of its execution. Okay, so how many states technically would you think that this state machine has? 4? 3? It technically has 3 states. We call B an OR state because it's like If you're in B, you're either in C or D. So it's not really a state, it's a pseudo-state, if you like. So this machine technically has 3 states, but keep that in mind. It can have 4, as we'll see soon, depending on if we remember the refinement, where we are in the refinement. Okay, so if we're in C here, for instance, if we're in C, if G1 is present, so we're in B, we're in C, I almost need 2 fingers to do this, and let's say that both G1 and G4 are present. Okay, so this guard is enabled, and also that means that guard is enabled here. What do we do? Well, clearly we have to produce output A4 according to that transition there, and we have to produce output A1. So we can write that as a sequence of operations that happen, A4, A1, or A1, A4, depending on some sort of ordering that we choose, and hope that these things aren't contradictory. Okay? We could get a case where, you know, this is setting one output to 1 and setting the same output to 0, for instance, and then we get a big problem. Okay. Right, so let's look at a trace here, an example trace to see what's happening here. So for instance, and then remember how we draw traces, right? It's a list of the behaviour. This is a deterministic state machine, so it's a nice simple trace, one line trace for a set of inputs. So we start off in A, G2, the guard is satisfied. We go, whoa, to B, no, we don't count B, right? Because B is an OR state here. We enter C because this tells you that, right, enter here as the default. Okay, G4 happens, we go to D, then G1 happens. Okay, so G1 happens, but we're here. So G1 happens, and we go back to A. All right, but so what's happened inside this machine? This machine's gone back to A. Where's this machine sitting? Let's see. We get G2 again, and we go to the OR state B. Whoa, it's D. Ah, okay. There's some history involved here, right? It's like when we transitioned back to here in this state machine, right? This one was just left exactly where it was. It has a history. We've got a history involved here. If G3 and G1 are both asserted here, then we go back to A, and then obviously on next entry into B, we end up at C. Okay, so we are keeping track in this particular instance of a machine that we will, where we were here in the refinement state machine, the inner part of B, right? So this is what's called a history transition. And we indicate a history transition by a solid arrow. So you can see it's almost like by default we have a history transition on most refinements. Sometimes it's also explicitly written as an H next to the transition in order to make sure that you're just not drawing black-headed arrows by default and forgetting that that implies that there's a history transition going on. Okay, so a history transition implies that when a state with a refinement is left, here's a state with a refinement, it's left, here's a state with a refinement, it's left, that it's necessary to remember the state of the refinement. Now, what that means is this is, with the history transitions, this is a 4-state state machine. Okay? When we flatten it out, it'll make much more sense. So just like in ordinary compositions that we've seen so far, all the other types of compositions, we can flatten out the state machine diagram. But what it does is it blows up the state space. There's a reason for doing this. It's to simplify the model, right? To compactly represent a lot of information. Once we flatten it out, we can observe the behaviour really nicely, but it blows up like crazy, as we'll see. So let's assume we've got history transitions now. So we've got to remember the state we're in the refinement, even as we transition away from the state that is the refinement. Okay, B. So remember, here's our diagram here. This is a history transition now. These are in. And this is our flattened model. We have 4 states, right? So if we're in A and C, right, and we transition, we're going to assume we're defaulting in C, right? And G2 comes in, we go to B, and we represent that as BC. Right? We have to keep track of this as an independent state, because if we then get G4 happen, and make sure that G1 is not also happening, we go to BD, so we're still BD. If G1 happens, but we don't have a transition inside the refinement, we go back to AD, remembering that if we get G2 again, we're going back to BD. We're not going back to AC this way, okay? Which, without the history transition, right, we would always, anytime we enter the refinement here, we always go to C. It's only a 2-state state machine, so it's not as clear as if we had a lot more states in here. Okay. So you can see what the refinement does here. The refinement makes a complicated state machine, when it's all flattened out, look nice and neat and compact, and it describes exactly what's going on, in particular indicating that there's a history, because we need to know that. This is where this is maybe not so obvious, but remember that the composition, well, I won't say remember, for the history, if you have a history of the refinement, the composition is the cross of the 2 amount of states, the state space. So, in other words, 2 by 2. What if our little state machine here had 4 states, and that refinement had 4 within that? It becomes a flattened 16-state state machine. So it starts looking horrible when it's flattened out. But that's why we make refinements, to make it look nice. A 4-state state machine with little 4 states in here is much nicer than a 16 with transitions all over the place. Okay, another important question. What's the opposite of the history transition? Well, it's called a reset transition. And it's indicated by an open arrow or a white-coloured arrow, but it's explicitly indicated differently to a history transition. And, as you may expect, what that says is that when we enter the refinement, we always go to C, no matter what. It doesn't matter what state we were in here. When we exited the refinement, next time on entering, we go to C. And in the trace, you can clearly see the difference is, so we go A to C to D, back to A. In the history, we go back to D because that's where we were for those inputs. For the same inputs, A to C to D to A, back to C, right? We default to that every time. Okay, so down the bottom there, reset transition implies that when a state with a refinement is left, get out of it, you can forget the state of the refinement. And that collapses the state space down a little bit, right? In particular, it's much more visible when you flatten it out. If you flatten that out, in terms of all the possible transitions now, it's only a 3-state state machine, right? As we kind of intuitively thought before, right? That it just looked, if B was ORing together 2 states, couldn't we just sort of shove them in? We can if it's a reset transition. Okay, so there are fewer states because we don't need to keep track of what's going on in the refinement. And that makes obvious sense too, right? If you don't need to track stuff, we need less state space to do that. All right. There's another important type of transition we have to mention as well, and this is important for our interrupt controller model. And that's the notion of a preemptive transition. What's a preemptive transition? Well, firstly, it's indicated by this little red dot. And what it does is it specifies that a guard should be evaluated before the current state refinement reacts. So it's defining some sort of ordering here in terms of reaction. In particular, so here, right, we would actually be checking G1 before we check if there's any transitions going on in here. So it's like almost G1 has precedence ahead of any of the other guards that are changing states in the refinement. And you can see what that does is, if you look at the flattened version of it, right, it simplifies it even more, right, because it's basically removing conditions that had, with G1 that had additional stuff on it, down to just transitions with just G1 on them, okay, because G1 is it's preemptive over what's happening inside the refinement. Okay, so we've got three new types of transitions now: a history transition for refinement, a reset transition, and a preemptive transition. All right, let's get back to the task. That was our crazy four-state interrupt controller, but if we model it as two states, we can actually compactly represent all of that info using two of those things we've seen: history and preemptiveness. And it becomes a two-state state machine with refinements in both of the states. Beautiful. So it's a hierarchy, right? A top-level two-state state machine. And inside those refinements are A, B, C, D, E, right? 3 and 2 states. Now, so remember that's preemptive, and these are histories. So we might break it down instead of the code in terms of its refinements in terms of their state diagram. So we came up with these before and they were fairly realistic, but now it fits in the grand scheme of things within a higher level state machine. So how do we describe what happens? Well, if you're inactive, so we're in the main loop of the C code, right? What does preemptive mean? Preemptive means the guard is evaluated, right, and a transition taken before anything in the refinement. Makes sense. An interrupt comes in, you don't keep processing the main code, right? You basically change state, and we're defining state as being active in the ISR, right? You're either active in the ISR or you're inactive out of the ISR in the main code. Okay, so preemptive, perfect. That models an interrupt fantastically. And we enter the ISR here, right? And whoa, what's going on here? There's only 2 states. We don't need an idle. I won't go back super far, but you remember initially we had to have some sort of idea of an idle state, that it's in a state where before it's not D or E. But using the reset transition here, we can always say, well, you're always coming into D every time, right? Every time. We're not going to be left hanging about where to go or anything, right? It's always into D, right? Start at the top of the code, work your way down. So we've condensed this down now, got rid of that extra state here. Right, so, and the last thing is we have a history transition here, right? So we need to remember the state of where we are when the transition happens. And we've got 2 controls now, or guards, assert and return, to indicate whether or not we should be taking the ISR or we're coming back from it, right, to signal some external stuff. Okay, so let's get back to the question. Now that we've modelled this in terms of a top level with some refinements, and we've been clear about when guards are taken by being preemptive and resetting, and how you enter the refinement, let's get back to the question. Is state C, so getting out of the while loop, is that always reached? Is it reachable? Okay, there's one way to find out. We're going to flatten that FSM out enumerate all the possibilities, and essentially this is like doing a trace analysis on it, essentially. So let's flatten all of this out now. So we have A, well, we could call that inactive if you like, right, because it still doesn't necessarily exist. We enter that, right, because we have a reset transition, we go straight to D every time, right? If we're in B, we enter that, the ISR, we go to D every time. If we're in C, and we enter that, we end up at D every time, right? Here's the interesting thing. Assert is our input that's telling us that an interrupt is happening, okay? In this case, it was a timer ticking away, and what we'd be doing would be we'd be decrementing the counter, right, in the ISR. Remember, if you're in D or E, you're in the ISR. Now, the interesting thing is you can kind of see how it's laid out here, right, that you've got state A in main and all the possibilities, state B, state C, like this. We can actually analyse this now and realise that there are cases that can happen where you may never end up in this entire column here. Now, this column are states that are composed of being in state C in the main code. Oh, why is that? Well, just look at the transitions here, right? So these are default transitions, right? Anything that's dotted is a default transition. And a default transition is followed if none of the other guards are active and a reaction has occurred. Okay? Typically, the default transitions are used for loopback often. Okay, so what happens here? Well, what happens if assert, right, in interrupt is coming in, right? Interrupt comes in, okay, you service it, whatever. Interrupt comes in. Or even over here, right, we're at B part of the code, interrupt comes in. So if we look at this diagram, we can actually conclusively say that if assert is repeatedly asserted, right, infinitely often, that we will never actually be able to get across to here in order to reach part C of the code. Why? Well, because this branch is taken pretty much every time, right? Bang, 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 or these branches here. Okay, this is default transition. So if this guard is asserted, it takes precedence over any default transitions. I say asserted. If this guard is evaluated to true, I should say. So this is really interesting, right? We've worked out how to model a piece of C code or two pieces of C code and how they interact in terms of refined states from a top level and then obviously going into the refinements here. In order to do that, we have to define preemptive and reset and history transitions. But when we do that and flatten it all out, we can actually fully analyse this now and work out that there are conditions under which that piece of code, the C part, which is getting out of the while loop, could not happen. Now, this is a trivial, well, not trivial, it's a simple example. You might even think, back to the C code, well, what happens if a lot of interrupts just keep coming in and it just keeps running the ISR forever, right? Fair enough. Maybe you might realise that it would never get to C. But for much more complicated cases where you can take this diagram and go and show someone and say, it will never get down here, that's, right, that's a formalism, right? That's what you can do. You can conclusively prove that. Why is that important? If this is a safety critical system, right, you can't just sort of say, oh, I've looked at the code and I think it looks like it works and I've enumerated some of the possibilities, but this is a formal analysis where we can do that. We will look at this in more detail when we do reachability analysis. We'll actually formally go through all of this. We kind of skipped through a trace here to just get the point across. All right, so we now know a bit about composition. Okay, so we've got different models of composition. in terms of synchronous composition, asynchronous composition, the various forms of interconnections, the spatial way of doing it. And now we've got a way of doing it in terms of hierarchical FSMs. Okay, we can always flatten them out, but there's a reason why we necessarily don't flatten them out, because they become complex. We put it in a machine to do it. We have to be super formal about this. This might look so pedantic about having bubbles with different colours